Okay, so let me set up the screen sharing.
I think, Krashen, I think you're still screen sharing, if I'm not mistaken.
You can probably do the unsharing thing, Oliver, as a host. Or allow...
I can only press share. It doesn't look to me like I'm sharing.
No, now it's good.
No.
Thank you.
So you can see, people can see my screen?
Yes.
Okay. Thank you, Argo. Thank you, Oliver. And thank you, Christian. Very interesting work. We'll have, I think we have budgeted time at the end for questions. I certainly have questions. So yeah, good morning to all in Denmark and good afternoon to people here. My name is Dayadeep Monder and I'm in the Department of Energy Science and Engineering at IIT Bombay. So the work I'm presenting here is the work done by one of my master's students who graduated last year. And this is on reversible solid oxide fuel cells. Well, we should call them solid oxide cells because you run them reversibly. And I know that people here, especially at DTU, have worked on these systems. Actually, there's going back to Mogens and his students, and perhaps even before that, there's a lot of work done in DTU, at DTU, on these systems. But I'll just share what we have done briefly. So, okay, there we go. So just quickly going through this. Let me see, how do I change laser pointer? Okay, so for large scale storage, and this is a graphic that we've borrowed from Professor Barnett's group. So you can see that, you know, this is the system and there are tanks. The tanks up here on top are the important ones where you have one tank for fuel and one tank for used fuel, which most people call feedstock. So if you follow the red arrows are fuel going into these cells and stacks and being converted to electricity. So if you have the hydrogen in the fuel and the CO in the fuel being electrochemically oxidized. And on the other end, you have oxygen being reduced. And the oxide ions go across and you produce electricity. The used fuel goes into the feedstock storage tanks. And if on the other side you want to deal with pure oxygen, you can. Some designs work with pure oxygen, some designs work with air. So if you're dealing with pure oxygen, then you can have a pure oxygen tank over here. So the idea is that one can easily compute the round trip efficiency, which is an important metric. How much energy goes in the denominator, how much energy you can retrieve in the numerator. Yeah? Because when you have excess, when you have renewable energy on tap and you want to store it, you follow the green arrows. So you're supplying electrical energy to convert what's stored here, the used fuel, to convert it back into fuel. And on this side, you'll be producing oxygen. So that's sort of the cycle. And the round trip efficiency, as I was getting to, is an important metric. You want that to be as high as possible. So if one assumes that the charge that you're sending in is the charge that you are getting back. You scale the system that way, then what you're left with is the operating potentials in the charging mode versus the discharging mode. So their ratio will decide what the efficiency is. And this is not surprisingly a function of temperature, pressure, and composition of what you're dealing with. So if we look at the plot on the left, you can see it says maximum round trip efficiency. What this means is we are doing a thermodynamic analysis. So we are assuming that our devices are working at maximum efficiency. So the device efficiency does not come into it. We're looking at the maximum thermodynamic efficiency based on the composition, temperature, and pressure. So kinetics does not enter into it. Kinetics, we'll deal with the kinetics later on. So here you can see that even with that assumption of perfect fuel cells and perfect electrolyzers, with the given constraints that we have, if you're using only hydrogen and water vapor, your maximum round trip efficiencies are fairly limited. But if you allow yourself to deal with some carbon containing fuels, so reformed methane is sort of a classical example. And these are the parameters which define the composition there: hydrogen to carbon ratio, oxygen to carbon ratio. Then you can get decent round trip efficiencies, and they're functions of temperature. The lower the temperature, the higher the efficiency. That's just how the thermodynamics works. On the right-hand side, you can see how the efficiency varies as a function of pressure. So as you can see fairly clearly, the efficiency increases as you increase the pressure of your stack. Now, having said that, we wanted to check what happens when you are dealing with real fuel cells, real electrolyzers. So real devices where the potential that you operate at depends on the current. And therefore, you have to account for all the potential losses when you're operating in discharge mode and the additional potential that you need to supply when you're operating in electrolysis mode. So we are accounting for all the physics, which is flow, mass transfer, fuel chemistry, electrochemistry on both sides, and heat transfer. And these are, so this is the fuel chemistry that we are accounting. So these are overall reactions for methane reforming and the water gas shift reaction, but thermodynamically reversible kinetic expressions. And these are again the fuel oxidation reactions that we are accounting for. Actually, a caveat here: in the current model, we're not really accounting for CO oxidation. So the CO is used through the water gas shift route, where you just produce additional hydrogen, and it's the first reaction here, which is essentially modeled, and oxygen reduction on the other side. So this schematic is a good one, which shows you what the device looks like. So Christian mentioned the MEA. So the MEA in solid oxide systems this is what it looks like. Usually the fuel side electrode is thicker because that provides the mechanical support. And the black layer in the middle is your electrolyte. And this layer below is your air electrode. Okay. So now here are some results from the kinetic model. So here we are implementing the full physics, which I put down in the previous slide, with one condition that here we're only looking at hydrogen water vapor mixtures. right?
Sorry to
So
interrupt, Dayadeep. Somebody
Sure.
says presentation is not visible. Is it visible for us?
Yes, yes. It is.
I can see it, right?
Okay, then it's okay because somebody wrote right now that presentation is not visible. Thank you. Sorry, interrupting.
yeah,
Please
no
continue.
worries. Perhaps just the window moved somewhere and they'll just have to locate it. Yeah, okay. So the plot here tells you how the current changes along the length of the device. So this is core flow for fuel and air going from the left to the right. And this device is what we're modeling here is a 10 centimeter long device. So you'll see that the current in the beginning is higher than the current at the end, what we would expect, right? The compositions are such that you have a higher current in the beginning. And the effect of temperature can be seen that it affects the temperature affects the kinetics, the temperature affects your conductivity of the electrolyte membrane. So at higher temperatures, you have high rates of reaction. And for example, the highest here is this purple line, the lowest is this blue line. And this shows you what is the average current density. So that's just the average of these curves that you see on the left. The third row gives you something called utilization. So how much of your fuel and oxygen that you're putting in, how much of it are you using up? So those numbers will affect performance. And next slide is showing you again, the left-hand plot shows you the performance curve in both modes, in electrolysis mode on the left, fuel cell mode on the right. So you can see the negative currents represent electrolysis mode, the positive currents represent fuel cell mode, and how these change for a given composition, how these change as a function of specified temperature. So this model that we are looking at right now in this slide, this is where it's an isothermal model. So you're not solving for the energy balance yet, but you can clearly see the effect of temperature. And this right-hand plot shows you, again, the performance curve with varying composition. And this dashed line is a very important feature of solid oxide cells, where in electrolysis mode, if your cell potential is below this, so is between this point and the open circuit potential, it's easier to see it on this plot. So if you are in this region, below 1.29, I think is here. In this region, you will need to supply additional thermal energy into your system to keep the system running, thermally alive. Above this, you're producing excess thermal energy, and you don't need to supply additional thermal energy. So that's an important feature of these high temperature systems, electrolyzers. And it impacts the efficiency that you can expect from your system, because it's this potential. It's the potential on the electrolysis end which goes into the denominator. So the higher the potential that you want to operate at, or you're forced to operate at, the lower your efficiency. So you want that to be as close as possible to this gray line from above. Okay. And now, I'm just walking you through the stages of the model that we developed and then solved. So up until the previous slide, we were looking at an isothermal model. In this slide, I'm giving you results on the non-isothermal model. So the energy balance equation comes in, and this is where that point I made on the previous slide is again sort of emphasized, where you can see that when the potential, so 1.14 and 1.24 are these two lines, as you go along the length of the reactor, if you're operating at that temperature, at that potential, your temperature of the device as a function of length comes down. Yeah, so your operating temperature is coming down. Only when you are at the thermoneutral voltage do you see a stable temperature through the device. And of course, if you're above that, then as expected, the temperature rises above the inlet temperature. And the right-hand plot just shows you how the current distribution changes as a function of length in this non-isothermal model. So having done that work, we said, okay, now can we compute the round trip efficiencies with the condition which we just spoke about, where we are operating at the thermoneutral voltage or above the thermoneutral voltage, because otherwise the stack is not going to be self-sustaining in terms of temperature. So you can see that at different temperatures now, these are calculated average temperatures for the cell. And you can see that even for, we saw earlier that the lower temperatures are more favorable in terms of round trip efficiency. So even at the lowest temperature reported here, we can, of course, do a little bit of extrapolation, but these are computed values. The round trip efficiency is not great. So this is just to emphasize the point that if you're going to do large-scale energy storage using such devices, then it's much better to use carbon-containing fuels and feedstocks. So now this point is sort of underlined on this slide, where you can see that the round trip efficiencies now are indeed much better. And this again, now we're trying to probe temperatures even below 600 degrees Celsius. On a computer, it's all easy, right? I mean, it's as long as your model behaves itself, you can do it. And we tested that our model behaved itself. We tested it in many, many, many ways. So here you can see two effects. One, as you increase temperature, you should expect a lower efficiency. But if you increase pressure, you should expect a higher efficiency. However, there are trends here which show you that perhaps even 2 bar is good enough, depending on the temperature that you want to work at. So that's one message. Okay, pressure and temperature matters, even when you have carbon-containing fuels. With carbon-containing fuels, you can expect higher efficiencies. Another thing which will help you on the efficiency end is if you have the flexibility of choosing your currents during charge versus discharge. So if you allow your charging current to be higher than the discharging current, you have an efficiency advantage. That's the main point of this slide. And of course, you see the pressure and temperature effects here. Then we said, okay, that's sort of a cell level model which we can with some assumptions expand to a stack level model. Now, what happens at the system level? Because at the system level, as you can see here, and this is a simple system, you'll have these two tanks. From these tanks, where you will be storing your feedstock and fuel at temperatures which are lower than what you will be using them, at the temperatures you will be using them. So you'll need heat exchangers, right? So you'll need heat exchangers to bring up the temperature before you send it to the stack. for both of these things, for feedstock as well as fuel. For the air as well. So you will have to, so this system, going back to the first few slides where we said you could use either air or oxygen. For the time being, we are assuming we're using air to keep the system simple. So if you're using ambient air, you'll have to compress it, then you'll have to heat it up, and so on. So this is as far as systems go, a fairly simple system with not too many balance of plant elements, right? There's 4 heat exchangers and 3 compressors. So we said, okay, let's build this on the computer, obviously, and check for what sort of efficiencies we'll see. So what you see here, the arrows show you the direction of the streams in discharging mode, that's fuel cell mode. This shows you the arrows showing the directions for charging mode, which is electrolysis mode. Yep.
We should start wrapping up because we are a bit over time now. Yeah.
Sure. So these are sort of the key takeaways. Okay. So the main point I want you to take away is that the stack level efficiency was approaching 80%. But for the simple system that we just defined, you're down to about 44. Okay? So obviously there's a lot of room for improvement here. These tell you, okay, what were the power outputs and inputs. Okay? So here I'd just like to reiterate the main messages that we've been able to build a fairly simple model. By the way, this is built in Python. So this is completely open source software and runs in the order of minutes. It doesn't take more than minutes for computation time on fairly simple computers. So these are some directions for taking this. How do you modify the systems design to give you better performance? So with that, I will close and go back to Orgo.
Thank you very much, Dayadeep. Because of short time, let's move on to the next speaker, Dr. Harish Lakhotia from Stistel. And then we can take over the questions in the panel discussion time. Thank you. Hi, Harish. Probably have to switch the screen that you share into a different one.